Okay, so good morning, good afternoon, everyone. Today we will have a seminar by Adam Burrows that is going to tell us about the latest advances in supernova modeling and supernova simulations and the connection to the neutrino emission. So yeah, I hope this is of interest for the full group here with many new models that are coming in the 3D dimensional space, and yeah.
Thank you, folks, for giving me the opportunity to talk about some of the work we've been doing over the last few years. I give credit, of course, to my collaborators noted in the bottom left. There are others as well, but these are the major ones. I'm going to summarize some of our results, and I'm going to try to cut a lot of things. However, there's going to be a fair amount. And so in the beginning, I want you all to think about what you think is the mechanism of core collapse supernovae. What image do you have when a massive star dies? Give you 5 or 10 seconds to think about that. So what picture do you have? And now with my talk, I want to challenge all that. As people know, the supernova remnants and all other indications for core collapse supernovae, and that's what I'm going to be focusing on, of course, indicate that the explosions are not spherical. There's very great asymmetries, and that's indicated in this picture of Cassay. On the left, you see green, that's the distribution of iron inferred from X-ray data, and then red, which is silicon. But the distributions are very aspherical. And what I'll contend is that that certainly is fundamentally connected with the aspherical, inhomogeneous nature of the explosion itself. Now, as you well know, I'm sure there are lots of different types of supernovae. I've circled those that are associated with core collapse unambiguously. And so the majority of supernovae are these core collapse, massive star death explosions. The tool that we put together, and we put it together from scratch a number of years ago, is called Fornax. We've done about 40 state-of-the-art 3D simulations, carrying many of these models to late times, sometimes 10 times longer than most other researchers. We have about 250 model seconds actually calculated, which is more than the rest of the world combined. And most models explode naturally. I'll contend, in fact, that, at least in broad outlines, certainly to zeroth order, the problem of core collapse supernova explosions and their mechanism has been solved. And it's the neutrino mechanism aided by turbulence most of the time, with many components that are quite interesting. There are differences between low mass progenitor explosions and high mass progenitor explosions. We form black holes a fraction of the time, although what fraction that is still a matter of contention. And some of those black hole formers actually give you supernovae. So the idea that all black holes formed in the stellar collapse context are failed supernovae, I think, is completely false. Although proving this observationally is going to be interesting. There's going to be a lot of eye candy in this talk, but there's also going to be a few words, and I just want to mention a few general concepts. On core collapse, you leave behind a protoneutron star in which the material is optically thick to neutrinos. And so there's a neutrino sphere whose radius depends on neutrino type and also on energy, but is on the order of tens of kilometers generally. At bounce, the shock wave that's formed, it's a spherical piston, actually generally stalls or slows down quite a bit. And it's re-energized by the neutrinos that are coming out from that protoneutron star, depositing maybe 5 or 10% of the energy before they leave in this outer envelope. And the explosion is an explosion of the mantle of the protoneutron star that might become a black hole later. By the way, you never form a black hole directly. That's not possible in the Chandrasekhar collapse context. It has to go through a protoneutron star. Hence, you'll always get a significant neutrino signal. Even if you form a black hole, you'll get significant gravitational wave signals as well. In the 3D context, you can get simultaneous accretion and explosion. So the breaking of symmetry is important. Where you might explode a little bit more in one direction, you can accrete due to infall in the other. Even though the shock wave has gone through that material, it doesn't reverse the velocity. And so that material can continue to accrete, and that gives you an accretion luminosity component at the same time as it's exploding. In spherical symmetry, when you explode, you'd explode spherically, and that fallback would be rather insignificant. And that would mean that you turn off a lot of your engine that is driving the explosion, which is the neutrino emissions. And so you don't get the accretion component, which dominates for the early phases. The actual structure in the protoneutron star and before it's actually formed in the progenitor, the Chandrasekhar core varies quite a bit from progenitor to progenitor due to stellar evolution effects having to do with the rate with which neutrino cooling cools things and the nuclear burning rates and the redistribution of energy. And so you get a thermally supported Chandrasekhar core that can be from 1.2 solar masses to 2 solar masses. And that structure maps directly into the outcomes, whether things explode, whether you get black holes, all these sorts of things are connected with that. And I'll repeat that in the context of compactness in a bit. The code includes quite a number of sophisticated things. The neutrino matter interactions, all aspects of neutrino matter interactions except neutrino oscillations, and I'll, if I have time, show some of that at the end, are included. And some of them are fairly sophisticated, but some of them are still ambiguous. And so I will say at the outset that this is not the final word. There's complications in every aspect, but 50% of the complications are in the mapping of massive stars to that central structure. And so the evolution of massive stars is not a converged problem, is not a solved problem. One of the major breakthroughs in all this is the ability to do many calculations in 3D and make a few mistakes along the way. In the past, they were very, very expensive. And you could make a mistake, and after a year, you find out, and then you'd have to do things over again, but you may not have computer time. The code we've put together, again, not perfect, addresses all the issues except neutrino oscillations, and is rather fast. It's about 5 or 10 times faster than competing codes. The slowest part is actually the energy redistribution from the neutrino matter scattering. And so it's like Compton scattering, but we're trying to speed that up. Okay, so we can do many 3D simulations in a year now. And as I mentioned, we've done quite a few long-term 3D simulations, and we've done about 90 in all, 30, 40 to late times. And so what we've been able to do is predict or at least calculate to the asymptotic state, which is after 5 or 8 seconds or something like that for some of these models. In comparison, most people don't go beyond 1 second in their simulations or half a second in their simulations, with very few exceptions, usually dumbing down things at later times. We've been able to get the explosion energies, the black hole, whether black holes form and in what context, the nucleosynthesis, the morphology of the blast, the kicks, because there are recoils in these asymmetrical explosions, and many of the signatures, including the neutrino signatures. That core, and I should stop right now and see if there are some questions. Any interesting questions at all at this stage? Okay, well, feel free to ask. And so on the left-hand side and the right-hand side are distributions of those initial Chandrasekhar progenitors, where the density goes from about 10 to the 10 grams per cubic centimeter down. And I just want to call your attention to the range of density profiles, and that some of these models have a sharp drop in the density. This is versus mass interior, so Lagrangian coordinate, half a solar mass, 1 solar mass, 1.5 solar masses, 2 solar masses, etc. And some of these models have a very sharp drop. Some of them have a shallower drop. And this is referred to in the latter case as a high compactness if you have a shallow drop. And if you have a steep drop, it's a low compactness. And I'll refer to that going forward. That's only one parameter, and these profiles are multi-parameter, but this is a 0th order thing. And we'll see that many of the outcomes are connected with the compactness. In other words, the structure of the Chandrasekhar core will map into the outcomes the mass of the neutron star left behind, all these sorts of things. These two plots show two different renditions of massive star evolution. On the right-hand side is from Kepler, on the left-hand side is our calculations of the MESA code. Now, qualitatively, they look similar, but this is the same mass range, and this is for solar metallicity. But the models are actually different. And so there's some of them are very different at a given mass, a given ZAMS mass. So just keep that in mind. Okay. And so on the top left, you see that this is the average shock radius versus time. And you can see many of the models sort of settle down, slow down, they bounce around a little bit, then explode. And to 90% of these things, we can figure out whether they explode ahead of time just looking at the cores before we do the simulation. There's all sorts of subtleties in that 10%. And this is the same sort of plot, but on a much larger scale. Here's 5,000 kilometers. And you can see these models are exploding, and some of them don't explode. And these are models that don't explode, but will still form black holes. And we have models that do explode and form black holes. This is a picture of just a snapshot of the protoneutron star. It's just about 100 kilometers top to bottom in this. And this is an isodensity surface. And in the interior, you have protoneutron star convection, which is important in boosting the neutrino luminosity a bit to help in the explosion. If you do it in 1D, it's not there. So you can't do this in 1D. And then the outer region is very turbulent and convective, and it's that outer region that explodes. The shock wave is actually on this picture exterior to the frame. And so I want to show a movie. And this is the techno version. I don't know if you can hear it. And this is just an example of a core collapse. And this is just after bounce. And so you see matter falling in, and that blue line, that blue region right there is the shock wave, and it's a stalled accretion shock. So eventually it explodes, and then you get this Sauron's eye in the interior, which is the protoneutron star. And if you look carefully, you see that that isodensity surface is actually shrinking. This is the Kelvin-Helmholtz phase in the protoneutron star evolution. At the same time, though, as the neutron star is forming, the blast wave is moving out through the rest of the star. But you see that there are all sorts of bubble structures that are associated with that turbulence and the character of the explosion in that turbulent case. One big bubble starts to lead things. And so look at the top bottom right, we have a collection at different times as we go up in ZAMS mass of what the explosion looks like in the first seconds, 4 seconds, 2 seconds, 5 seconds, etc. And you can see in all cases, there's no spherical distributions. The isosurfaces you're seeing there are actually Mach number. The red is positive and the blue is negative. And you notice in those other three plots, for example, here, there's infall. And so this thing is exploding at the same time as some of the stuff is falling back in. And that's connected with this simultaneous accretion and explosion. And it's connected with that accretion giving you continued neutrino emissions that continue to power the explosion. Any questions at this stage? No? Okay.
Looks like there is one.
Good. Just ask it.
Yeah. Hello, Adam. Thanks for the presentation so far. I have a question. Like, it seems like there's some structures that look like hair or like bundles of. Can you explain that in a?
Oh, that was just.
Yeah.
You mean that?
Yeah. What is that?
Yeah, that's just the mass trajectories. Those are Lagrangian tracers of the background fluid flow. And we put in an arbitrary number, and those are tracers for 50 milliseconds each, just to give you a sense of the tangled nature of the trajectories that are being followed. Does that make sense?
Yeah. Okay. Thank you.
Mm-hmm. And so we get all sorts of final state products, but we also get correlations between some of these things. Correlations, for example, between the supernova energy and the nickel production. Correlations between the neutron star mass left behind and the explosion energy. So I'm going to go through a lot of that. This is the baryon mass versus time, where the time is logarithmic. This is 1/10 of a second, 1 second, 10 seconds after bounce, where bounce, again, is when you first exceed nuclear densities and you start to rebound. Happens very quickly, so if you get it to within a millisecond, that's perfectly fine. And each of these lines is one of the models. And you can see it's going from 9 to 100 solar masses. I'll call your attention to these purple lines here. These are lower mass progenitors. The stars indicate when things exploded. And you can see that the baryon mass just sort of flattens out after a certain time. Some of these are flattening out over here at a fairly high baryon mass. The gravitational masses are correspondingly smaller, and I'll go that. Yeah. Shantanya.
Yeah, yeah.
Yeah.
So, yeah. So you have assumed that the final remnant is a black hole, okay? Now, your own thesis advisor had given a colloquium in fall 1974 at MIT with the title Black Holes Flunk at MIT. And now some people are talking about boson star, gravistar. So are there signatures after core collapse of supernova which can help us distinguish between black holes and these, I guess, alternatives to black holes or black hole mimickers?
Maybe. I don't put much credit in those alternatives. So what I'm going to focus on is just standard black hole formation, standard neutron star formation, and the standard stellar evolution context. But there will be distinguishing neutrino and gravitational wave and other signatures that will tell you whether a black hole formed or not. The neutrinos will be quite clear about that, and I'll talk about that later. But this is again giving you the hydrodynamic backdrop. And I'm sure my advisor meant well, but he's out of it. The fact is that the baryon mass actually flattens out. And so you want to do the calculations when that happens. And you see it can take a long time for that to happen. You also see these dash curves. These are all black hole formers. In particular, when that circle is there, that's when the black hole formed. We've continued these calculations after black hole formation, and I'll talk about that towards the end. Any questions here? Okay. So on the right-hand side, you see the compactness, that parameter that says whether it's shallow or steep, versus the gravitational mass of the neutron star left behind. And you see we get a trend. Now, whether the slope is correct, whether we have everything working properly, is not so clear, but this is what we get. And if we did one model, and these are all 3D models, if we did one model, we wouldn't know necessarily what the trends were, but we do many models, even if there may be noise in the calculations, stochasticity, because it's turbulent and it's chaotic. We still get some sort of trend. So this is a prediction of the theory that's emerging. This is an important plot, which shows the explosion energy versus time. 1 second, 2 seconds, 3 seconds, 4 seconds. And I'll call your attention to the fact that we're doing 33 million zones. We've tiled in 3D, 33 million different places. Each time step is between a half a microsecond and a microsecond. And we're doing seconds. So this is like 10 million time steps with 33 million zones doing 10 to the 16 floating point operations per step. And so it's an expensive proposition. But again, with the fast code, you can at least get some science done. And I want to call your attention to the fact that the explosion energy initially is negative. When it explodes, the blast wave becomes unstable, but you don't have enough energy to unbind the envelope. And so you have to keep depositing that neutrino energy over a long period of time, long in our case, again, is seconds, in order for this curve to flatten out. And it's only after it's flattened out that you know the explosion energy. People have used this term diagnostic energy. That's a fallacious term because they ignore the binding energy of the envelope, but they tell you that they get an explosion energy. That's completely false. It starts out negative when you include all the energies and the mantle is going to be ejected. And so you have to do these calculations till much later times to find out what the energy is. Okay. The explosion energy versus compactness, we get something like a monotonic curve. So again, this is a prediction that emerges. It's a little bit noisy, and we don't know the degree to which noise is actually wrong, is real, or whether it's numerical, etc. So there's still lots of work to be done, but we do get correlations. Here's the explosion energy versus gravitational mass. And again, the larger the explosion energy, the larger the mass left behind. Now, I'll caution that these models were all started with zero initial rotation and no magnetic fields. We're doing rotating models and magnetic models, but we haven't published those yet. The nucleosynthesis is quite significant, and this is one of the major drivers for nuclear astrophysics. And the electron fraction of the material, carbon-12 is half, oxygen-16 is half, alpha nuclei is half, and that's the middle thing. This is a log plot. And on the right-hand side is proton-rich, on the left-hand side is neutron-rich. And you can see we get a distribution, but a lot of it is proton-rich, with the dominant terms being at about 0.5. That factors directly into the nucleosynthesis. Now, I'm not going to go into detail there, but we get these various nucleosynthetic yields, mass fractions versus atomic mass. I could go into great detail in some of this stuff, but I'll call your attention to this peak over here, where some of the models have a lot of isotopes. This is near the first peak of the R process, and some don't. And we understand now why. It depends on the character of the explosion, which I'm not going to emphasize now because of time, but I'll certainly be willing to answer questions. The nickel yields versus time are given here. And the nickel is important because it powers a lot of the supernovae by its radioactivity. And so that's an important thing. And it's also the source of much of the iron in the universe. Type 1As are a major source, and this is about a third of all the iron, iron 56 in the universe. And you see, again, you have to calculate for a while to get to be flat. You get the nickel yields versus that compactness. Again, all these monotonicities or near monotonicities, which haven't been known before. And then again, nickel mass versus explosion energy. Whether the slope is correct and whether the details are correct is an open question. But I think that this trend is actually real. And in fact, the data are starting to indicate that, even though the inference of explosion energy is hard. Okay, titanium-44, for those who are following this sort of thing, is radioactive. It's been seen in Cas-A and 87A. And in order to get the nucleosynthesis, it takes a long time to do the calculation. I won't dwell on that, but you see, this is after 10 seconds. So you can imagine the effort involved in that. These are just trajectories of the bottom two, are trajectories of bullets coming out. We did 233,000 Lagrangian mass elements following the nucleosynthesis in all these things. This is just an example of the asphericities. Okay, black hole formation. Again, you want to think about what you might have thought was the character of black hole formation in massive star case. And what we find is that there are at least 4 or 5 channels of black hole formation, 4 of which I'll talk about here. And that also comes back to the compactness parameter. Now, if you look at the ZAMS mass, 10 solar mass, 20, 30 solar masses for solar metallicity models, and just this blue curve, this is what you get from the Suckbold collection using the Kepler code from Woosley and Hager and Suckbold, etc. And you can see the non-monotonicities here. What I will state immediately is that compactness makes a difference, but the actual mapping between ZAMS mass and compactness is very much in flux. If you do these calculations with a MESA code or other codes, etc., you don't get the same behaviors. So we can't say for a given mass progenitor at solar metallicity that's non-rotating initially in the inner core, what the final state is. We can say, given the compactness, more what the final state is. And that's something to consider. And so that's going to be something in the future. Okay. Here are, though, our helium core mass versus compactness, where the triangles are 3D models we performed a la 2 years ago. The red triangles form black holes. The blue triangles exploded, including this one way over here, which had the highest compactness of all. And somebody may have said to you in the literature, or someone may have told you that the low compactness is necessary for explosion and high compactness will form black holes. That's absolutely false. Low compactness can't get more than about 10 to 50 erg explosions. The average energy of the explosion of a supernova is probably half times 10 to the 51, going up to 10 to the 51. And some of them, a very small fraction, go up perhaps to as high as 10 to the 52. Those are probably MHD with rapid rotation. I'm not going to talk about those in this talk. But high compactness is necessary for explosion. And all the conditions in the literature that try to give you something for population synthesis and what gives what, et cetera, that say low compactness is necessary for explosion are false. They're just completely wrong. And no one who's doing real calculations now, Yanka, Couch, Kotaki, these people, and Muller, disagrees with that statement. Okay, so the black holes. This is that density profile where you have steep drop-offs. This is very small compactness. And here's shallow, very large compactness. And the for a range of progenitors. And this gives you the dash curves are those that form black holes. And these are their gravitational mass versus time trajectories in our simulations. The bottom left has a lot of neutron star formers. But as you get to higher masses, it's possible to form a black hole. And I'll call your attention to what we call channel 1 and here. We have two models there. And the stars and the circles. The star, again, is when the thing exploded. The circle is when it formed a black hole. And you can see the time between the star and the circle is very different for these models that are dashed, that form black holes eventually. This particular one was a 100 solar mass model at 10th solar metallicity. Its compactness was so large that the accretion rate associated with the infall, the collapse, was so large that it wanted to explode, and it did, but it was accreting so fast. Remember, simultaneous accretion and explosion, high compactness gives you high m dots, that it got above the maximum mass of a neutron star very fast. And so it tried to explode, and it did explode, but it didn't have enough time for the neutrinos to deposit the energy that it needed to unbind the envelope. And so it just sort of fell back, sent out a sound wave. So this it left a 37 solar mass black hole. In this channel 1 here, that's a 9 solar mass black hole, and this is a 3 solar mass black hole. And the difference is just the density structure, sort of like the compactness, where this time between the star and the circle was significantly longer. This is a log plot for this one here than this one here. And so it had more energy, and it had a little bit less accretion rate. So it formed the black hole later, and it exploded energetically. This had an energy of about 2.5 betas, 2.5 times 10 to the 51 ergs. This one was about 1.7 betas, 1.7 times 10 to the 51 ergs. This one we thought was going to be a neutron star. But if we continue the calculation for a long period of time, this is 100 seconds, we found that it actually formed a black hole, and it formed a 5 solar mass black hole. But a supernova observer would see an explosion that had half a beta, which is average or near average. It had nickel ejected. It had a kick that was 200 kilometers a second, which is okay. But it formed a black hole, which they may not have even noticed. And so what we predict is that a small fraction of supernova that people have seen and tried to characterize actually leave behind black holes. And black holes in an interesting mass range, and this is near the gap, the low mass gap, and this is in the gap. Okay.
This is really interesting, Adam. Can I interrupt?
Of course.
If you were to extend any of these models in time, these other neutron star forming models, would any of them have the same behavior as this channel 2 that you just showed?
That's a very good question, and we're wondering about some of these, and we're going to be doing this. But this one was among the progenitors around it. It was the lowest energy explosion. Everything at lower compactness and higher compactness had a higher energy explosion, and so we actually think that we don't know how often this happens, and that's one of the ambiguities in all this. But we think that it's a small fraction, but we don't know what that is. It's a very good question. I wish I could give you a decent answer.
Okay, thanks.
Yeah, this is work in progress. There's a lot to say, a lot more to do. But I do think that, and this was a 23 solar mass model, but if you look at the energy of the explosion versus the compactness, it went up, and then there's a little dip, and that had a half a beta when the others around it had about a beta. So and those are these around here. So I don't know the degree to which it was just chaotic, turbulent, little differences in the density profile that had an M dot profile that was slightly different. It requires a lot of work, but yes. Okay, so these are just those same trajectories where some of these black hole formers, the shock stalls, and these are the dash curves, and then they explode. Stalls, and they explode. These are fairly high compactness models. And this one exploded really early. That was the highest compactness one, but that fizzled out fast and left behind the 37 solar mass black hole. Okay, so this is an example of black hole formation. After bounce, the thing shrinks, it wobbles. That's the so-called spiral standing accretion shock instability. And you see, that's the shock wave right there, that veil on the outside. But you see stuff is accreting here, and it's accreting with an impact parameter and spinning up that inner region. And it becomes an oblate spheroid. And so there's neutrino emissions along the poles that are greater than along the equator, and you get neutrino-driven jets. We rotate the camera, and then a black hole forms. You see the black dot. But that was after 1 3/4 seconds, and that was long enough for the neutrinos that were being radiated during the protoneutron star phase to energize the thing so that it could eject the outer material, except for the 9 solar masses that fell back, most of which fell back through the side because of this breaking of spherical symmetry and simultaneous accretion and explosion. And you see this is entropy, and so it's hotter and it's very asymmetrical explosion, but it exploded. And exploded fairly energetically. Now, stepping back, we now look at our progenitors. There's an 11 solar mass here. There's a 15 solar mass, a 20 solar mass, 17 solar mass. And don't look at those numbers. This is just a collection. What you're seeing here is the model after 5 days, after more than a week, after fairly long times. This is in seconds. And what we've done is we take our fancy code, which is microsecond time steps, and we mapped it into the flash code and continue it in the flash code with a point mass at the center, thinking that that is converged. Okay? And so we have an inner boundary, and we watch the very asymmetrical explosion that comes out of the Fornax code evolve in the flash code. And that's how we can get to much later times. What you're seeing here in the purple is the nickel 56 distribution. The teal, light blue, is the hydrogen-helium interface. And in these models, that interface was a nice perfect sphere. And then you have the onion skin structure where progressively in, you get heavier and heavier elements, and there's going to be an oxygen region that's a shell. And then you go out and you get the edge of the helium core, which is this hydrogen-helium interface in teal. If you look closely, there's also green. That green is the oxygen. And that oxygen was a nice simple shell. And when the explosion came, it broke through. And the explosion has a lot, the dominant bubbles that are exploding generally have an excess of nickel. And so they act as bullets that can penetrate through those shells. And that's why the nickel is exterior to the oxygen. And there's a lot of mixing. Okay, I didn't want this in there. Okay, so here's an example of an explosion. The outer radius here, notice this is hours now, is the edge of the star. That's the blast wave. And there's a reverse shock that actually converges on the core. And you see this distribution of matter. And this is for one of the lowest mass progenitors we've calculated. And this has gone to about 4 days. Okay. I'll show you that again. So the Fornax calculation is right in the middle. The scale is now 10 to the 8 kilometers. You can see instabilities that generate in interfaces. This is over and above the original asymmetries in the explosion. So there are multiple mixing processes as blast wave goes out and encounters various shells and becomes Rayleigh-Taylor unstable. So you get mixing on mixing on mixing. And this is just an example of the distribution. The red is the nickel. The teal, again, is the hydrogen. And there's nickel exterior to the hydrogen and a lot of hydrogen in the inside. And we saw almost exactly this sort of thing in 87A. And it's very similar to what you expect in Cas A, even though Cas A was a type 2b supernova, so it didn't have as much of a hydrogen envelope as a red supergiant. And what I showed you here was the explosion of a 9 solar mass red supergiant. And this is just an example of distributions we get. And this is another movie. As the blast wave moves out, you can see how it's fracturing into smaller structures. There's still a large scale structure, and the dipole direction of the original explosion is preserved. And the red is again nickel, the bluish is oxygen, and yeah, this is we changed the color scheme unfortunately on this one. And this is just the nickel punching through the oxygen here in an early phase. This is only 430 seconds, and that teal mantle was a nice sphere, inner and outer radius, and at this time, the nickel has penetrated through, made a hole, and that just continues. So this is a rather interesting picture. This is done by David Katami, taking our models of the blast hitting the surface of the star, and this is what the light curve looks like. If you're at a fair distance and looking at the supernova exploding, and what happens is the bubbles that are associated with these instabilities, the fastest one hits first, and that's what you see first, and then you see others hitting the surface progressively. Let me do that again. And you can see there's a very asymmetrical explosion, and then you see those breakout bubbles. And this is, again, David Katami's work. He's not in our group, but he took our model and rendered this. It took a number of weeks to do this. And this is a sense of what an asymmetrical explosion in what would otherwise be a spherical star might look like. And that's an A-bomb. These are pictures of A-bombs after a millisecond, just for comparison. Okay, so I'm getting to the point where I'm going to start talking about the neutrinos, and I'm sure you're waiting for that. But just before I do that, I want to show a preliminary movie of these sorts of simulations with magnetic fields. And so this is the field structures. There's going to be core collapse. I have to get this thing moving. Okay, it bounces. You can see the shock wave right there in the B field distribution. And so right there is where the blast wave is. And then you see the tangle in here. That's because of the convection in the interior. So it's very convectively unstable in the interior. And that's due to neutrino-driven convection. It's the neutrinos that are driving that instability. It's like boiling water on a stove. You're heating from below. And the magnetic fields trace that. And so you can look in the inside, and the color represents the magnitude, and you can see the tangle, etc. Even though we started with a very simple dipole, because the turbulence tangles the field. And there's much more to this, but I'm not going to go into that here. Okay, so all of you are aware of the flotilla of underground, under ice detectors that exist around the world to detect supernova neutrinos. On the bottom of this slide are URLs where people can get some of our neutrino models. And so the first one is 100 2D models of the neutrino emissions as a function of compactness or progenitor. And you can just go through all that to get a full set of predictions for the full panoply of possible core collapses without initial rotation. The very bottom URL is the corresponding thing in 3D, but we have only 25 models represented here. But they're fairly similar, but they're a little bit more updated, etc. Okay, this I don't have to explain to you, but a super K is amazing. Hopefully it'll be followed by hyper K, which they seem to have money for. Ice cube is a huge volume. From the background variation in the neutrino absorptions and their consequences in the ice, you can get an exquisite light curve. which is the summed light curve. You don't get the energies of the neutrinos, you don't get the species, but you get a wonderful light curve. And the light curve says most of what's happening. Of course, there's Dune, and it's going to be in two parts. And there's Juno, which is now taking data. It's already started. This is the scintillator of 20 kilotons. Dune, of course, is a comparable size, but is liquid argon. Super K is a big swimming pool of water. And Hyper K will be 250,000 tons of instrumented water Cherenkov detector. But I don't need to tell you folks this. Okay. At preliminary, there's a paper that was led by Evan O'Connor, that compared various codes. And so this is the neutrino luminosity, electron neutrino luminosity, and mu neutrino luminosity, and tau and anti-electron neutrino luminosity versus time for different models. There's the Prometheus vertex model, which is this red curve. There's Fornax, which is this orange curve. And there are others, GR1D, and that's what this shows here. Flashes from Sean Couch's group. And they're fairly similar. There aren't huge differences. So the idea that the modelers are not coming to the same general conclusion, certainly vis-a-vis the neutrinos, it doesn't seem to be true. And so certainly qualitatively, everybody agrees on the signatures if you ignore neutrino oscillation effects. And we'll talk about that, I'm sure. There are some differences, and they depend on the difference in the numerical methods and also the neutrino matter interactions that are included. But by and large, there are great similarities. And this is also the comparison of with different calculations. And that's just so they're not huge differences. I think there are some models that are a bit off because of systematic problems, but by and large, the Garkin group, our group, Kotaki's group, not represented here, and early calculations of Barnhart Muller all agree by and large. Okay, and so these are examples of the neutrino signals versus time for different progenitors, and the thin lines in the top left are the 2D models. And there's a lot of noise in the 2D models for reasons we understand. In the 3D models, and these are the solid angle averaged. Solid angle average in the 3D case is much smoother. And you see that the 3D and the 2D are fairly similar qualitatively. But I also want to call your attention. This is the electron neutrino, this is the anti-electron neutrino, and this is the mu tau, anti-mu, and anti-tau bundled together. 2D and 3D, fairly similar. The 2D has oscillations because of the symmetry, in fact, that is smoothed out in the 3D calculation. But in various directions, and I'll end with that, you're going to get different emissions because the total neutrino emission is actually anisotropic. And that hasn't been published before. And so I'll call your attention. This is the breakout burst, famous breakout burst that people have talked about of electron neutrinos. It depends on the hierarchy. And we might talk about that. But you see that there's this plateau in neutrino emissions, particularly for the more massive progenitors. And then when the thing explodes, accretions subsides. It doesn't stop simultaneous accretion and explosion. And that diminution, the accretion, should be seen in the neutrino signal. And you see this in the anti-electron neutrinos and the electron neutrinos, and more or less in the taus. Okay. The average energies of the neutrinos, is given here. And you can see there's 10 to 20 MeV. The old calculations from Wilson, for example, had average mu neutrino energies that were 32 MeV. And if you had oscillation between 32 MeV average energies and 15 average energies, so that you could get a harder electron type or anti-electron type, you could help the explosion. The fact of the matter is, when you put in more modern rates of the absorption and emission for the mu's and taus and the electron types, etc., you get that the average energies are much closer, although you still see a bit of a hierarchy. The mu neutrinos are still a little harder. The anti-electron types and the mu's are very close, and the electron types are a little softer. Okay, in general. Okay, whoops. All right. Now this is from the 100 2D models. And I just want to show the nesting and compactness. Here's the electron types, the anti-electron types, and the mu's, taus, anti-mu's, and anti-taus, either one. And the blue is low compactness, and the red is high compactness. And you can see immediately, if you knew the distance to the supernova, which we better if it's in the galaxy, then you have an absolute neutrino luminosity in the different species. Again, modular oscillation, so you have to correct for that, however that is done. You can tell immediately what the compactness was, and you know if it explodes in the galaxy, what the star was, and so you get the star compactness connection. And we have predictions for exactly what that should be eventually, and certainly systematically. At higher masses, you have higher compactnesses, but exactly what the mapping is, as I said, is not so clear. Similarly for low mass. And so there are definite predictions that connect the neutrino emissions and the magnitude, which varies by a factor of 2 across this continuum from the high to the low. Specific predictions that can be verified. And there's a particular systematic from the blue to the red. Okay. The other thing is, if you look carefully, it's not quite the case, but there's a time to explosion versus peak that is roughly correlated. And so it's not quite the Phillips relation for type 1a supernovae, but there is a similar connection between a duration and a magnitude. And again, when they explode, there's a drop off. And so this peak here and the basic behavior of the drop off is a definite prediction of core collapse supernova theory. Okay. And here's some more examples. These are 3D models. And and again, this is all on the recording, so people can look at that at their leisure. Specific predictions, and note that these are logarithmic time. So that's why it looks a little strange. Logarithmic time. So these are broad peaks and then the explosion. And no matter what type of model, no matter who the modeler is, they basically get qualitatively the same behavior. Okay. One thing I want to call your attention to now is the difference between black holes and neutron star formation. The neutron star can't accrete up too much or it's going to become a black hole. When a black hole is formed, the neutrinos turn off to within a millisecond or so. So that is a definite prediction of black hole formation. Subsequent accretion is too thin, there's not enough emission, and then the material just falls in. You need that protoneutron star there to radiate the neutrinos. And so these are examples, 2 examples of black hole formation. No. Okay, where am I? I want to make sure. T40 black. Okay, now, yeah, okay. Now I'm going to talk about that in a bit. This one here, though, these models were models that never exploded. They were fizzled. The shock kept going, and then it settled in, and then the average energy of the neutrinos in that particular case is higher than the corresponding case of neutron star formation. You see these right here. These are 2 models that are going to form a black hole within a minute or an hour. Depends on the subsequent accretion. We're calculating that now. But they didn't explode, and we carried them out to more than 2 seconds. And in our game, if it's not going to explode in on that time scale, it's not going to explode. And so that is a distinctive prediction for this model of black hole formation where it never explodes. It just fizzles and sits there and will continue to accrete at the rate with which it's accreting until it forms the black hole. And it could do so for a long period of time. The average energy of the neutrinos that are coming out is higher than at the corresponding time for a neutron star forming. And you can see this difference, which is quite dramatic. Okay. Again, when a black hole forms, the signal turns off. And for those that formed and gave significantly, very energetic explosions that might have formed at 1.75 or 2.5 seconds after bounce, you're going to see the neutrinos. It's going to be a pretty strong signature, and then it's going to turn off. Now, the other thing, and this is compactness versus this is not a big deal. This is versus the total neutrino energy that's going to be radiated. So total energy radiated versus compactness. And the character of the explosion in the light curve is connected to the compactness. So you can check that. Total energy and then the light curve. This is gravitational waves. And now, there was a paper that was led by Lila Choi that looked in much more detail at the neutrino signature. The 3D stuff that are in this talk came from that paper, but there's also more. And so the height of the peak versus the time of peak luminosity is more or less monotonic. That was that pseudo-Phillips relation. And this is for different, so there's a lot of stuff to unpack in here. And then the peak height, remember those heights, there's a peak and then it exploded and then it settled off. The heights versus the gravitational mass are monotonic for black hole, for neutron star formers. So this peak height is directly connected to the gravitational mass of the neutron star left behind when you leave behind neutron stars. And then the radiated neutrino energy versus the gravitational energy radiated in the hundreds of hertz to kilohertz range is also more or less monotonic with one another. And that's because they all depend on the compactness, the accretion rate, and the vigor of the fallback accretion hitting the surface with the gravitational radiation coming from the oscillation of the core. It's astroseismology. That's the dominant source of the gravitational waves in the 100 hertz to kilohertz range. Okay, so this is something to keep in mind. The different models explode aspherically, and the neutrino emissions generally are also aspherical. And so these are mole-wide projections of the neutrino emissions for various models. And some of them emit neutrinos very aspherically. And so if you assume that the neutrinos you were measuring could be isotropically averaged, as if it's coming out the same in all directions, then we think that that would be wrong. Now, nobody else is really calculating this at this stage, so we'll see what emerges from the community collectively. But I think that that's going to survive. Exactly what the numbers are is going to be not only chaotic and stochastic, but it's still an open question, even when you have the right models calculated correctly. Some of the models are pretty spherical, but some aren't. This is the distribution of inferred isotropic neutrino energy radiated. Okay, and so you can see the inferred neutrino energy radiated varies from model to model. Now, these are the energies radiated by our models. It's not the total. It's our models out to 2 to 10 seconds, and the total will be out to a minute. So there's radiation still coming out, but we haven't included that here. But it just, as an indication of the distribution of possible inferred total energies over these periods of time, each one of which is published, each one is calculated to a certain time, you see a range. These aren't delta functions. Delta function would be everything is isotropic. Okay? And this is for the electron neutrino. This is for the total. Okay. Any questions at this point?
Oh, I do have a quick question. The plots, the anisotropy plots that you showed, those are integrated over the whole explosion, or those are time slices?
This is integrated over the whole calculation.
Okay. The reason I'm asking is, you showed this really, really striking video about 15 minutes ago showing these jets,
Yeah.
Which is very strongly anisotropic. So the question is, are there parts of the explosion that if we're misaligned with the jets, we could just miss entirely in neutrinos? Do you think we can say that?
Not miss entirely, not in the galaxy, unless, yeah, for those that are more asymmetrical, you get generally more asymmetrical neutrino emissions and more asymmetrical explosions for the higher compactness models.
Mhm.
The lower compactness models do get mixing, but they're not as asymmetrical as the higher compactness ones.
Okay.
This 9A model is a low compactness model of 9 solar mass. The 17 is a higher compactness model, and you can see the asymmetry. The 14 is actually one that formed a black hole. We don't know exactly why. We understand why that model did because of the structure we inherited from the Sukhpol collection of massive stars, but we don't know that in fact 14 solar mass models give black holes. 2/3 of the models in that mass range actually form black holes from about 12 to 15. And that's a controversial conclusion, which I don't personally credit too much because we just got what we got from those progenitors. And it may well be that other progenitors will make those explode naturally. Yeah.
So, are there correlations with the neutrino luminosity with the angular momentum or the rotation speed of the remnant? Maybe you showed this. I had stepped out for a minute or
No,
two.
no, no. These are initially non-rotating, but you're right. There is induced rotation. I want to do rotating models before I say much about any correlation there. But yes, there is, if it's rapidly rotating, that rapidly rotating black hole former was initially non-rotating, but the fallback gave it angular momentum and it became an oblate object. It left behind a black hole with a relativity parameter, a spin parameter of 0.6, can't get above 1. The other one in that family of channel 1 black hole formers gave a black hole of 0.1. So there's a range, and exactly why they did what, I think, is stochastic, and we haven't worked that out. My boast that we can do many calculations is set aside because we have to do many, many, many more, and it's still an expensive proposition, so we have to husband our resources. Okay.
Adam, just before
Yeah.
you continue, sorry, this is Jeff. Yeah, always fascinating listening to your or attending your seminars. So just kind of to follow up with what Segev was asking. I mean, well, actually, this is kind of more like an observation on what he was asking. I guess in the anisotropy, the mole-wide plots that you were showing, there was about a factor of 2 difference, it seems, in any given direction. So I think, yeah, I guess the statement that, I mean, we can do a factor of 2. We're not going to miss the supernova,
Right.
Probably. But connected with that, you made an earlier statement about getting the distance of the supernova.
Yeah, the distance the best measurement is from optical electromagnetic. You probably will have had in archival data, the progenitor. And there's a lot of good ways of getting distance in the galaxy that isn't so bad.
Okay, I mean there were of course some ideas about how to get that from the neutrino emission.
That's right, but if it's in the galaxy, which would have by and large have to be LMC, SMC within about 700 kiloparsecs, then use the electromagnetic. That'll give you real constraints on distance, and you'll get a secondary distance this way. But that would be model dependent, and I'm trying to check the models. So we are making predictions for once you get that distance, and then you infer the total neutrino energy radiated and the luminosities of these peaks. You can say what the compactness is. You can say what that density profile is, and you can predict what the neutron star mass is going to be, the explosion energy. There are all these predictions that are connected with that correlation. And so that's exciting on one side. If people understand that and really read the papers associated with this, we've published a few in the last few years that have all this stuff. And on the other, it's a little daunting because we're actually making predictions.
Okay, thanks. Yeah, I was also thinking in terms of just the real-time calculations or estimates of distance, which is not the problem that you're talking about. But because that can also help in identifying the star very quickly. Yeah, but that's a different problem.
It'd be nice to be able to get direction. That's
working on that.
Yeah, there are all sorts of ways, and people can talk about that if they like, but this talk is already long enough. So I just want to end with a little bit on the fast flavor instability. I'm assuming people know about neutrino oscillations. The neutrino oscillation effects in the supernova are not MSW, but can be these so-called fast flavor instabilities or collisional flavor instabilities. And how to incorporate this into calculations is still a work in progress. There's a lot of theory on this, but the theory is not well coupled to the theory of the explosions. But what we've done recently is we've implemented something from Sherwood-Richards called Box 3D that gives a probability of these types of fast flavor instabilities that I can embed in a classical calculation. Instead of doing fancy density matrix off diagonal calculations where I'd have a much more complicated um, uh, set of calculations to solve that would include the correlations in the neutrinos due to quantum effects. We're using this particular approach. And we've published 2 papers on these sorts of things so far, and we're doing a third. But I want to show some preliminary results. This is just the scheme, and people can look at that at their leisure. This is the difference in the neutrino emissions, 1D and 2D for the electron type. And this is a coarse electron, this is millisecond being dumped every millisecond, so that precursor bump over that is always there isn't there. And you see that the dashed is no oscillation and the solid is oscillation for the mu neutrinos, and that's the total. And then, so the dashed versus solid, and you can see green versus solid green versus dashed green, solid red versus dashed red. You can see the character of the differences in 1D and then in 2D. Now, the first thing to note is the differences aren't very large. The second is there are differences, and we want to work through that. And you can see this for another model. This is the 18, and these differences are starting to be interesting. You know, a couple of tens of percent. For the electron types and the anti-electron types, there's some interesting differences. Here's solid, which is with the oscillations, and dashed, which is without the oscillations. And the sum of these things is appropriate. So we're conserving total lepton number in these calculations. That's part of the scheme. And so when the mu's go up, the anti-electron types and electron types go down. But some of the models, things are pretty close. And then we can go into a lot more detail here. But there's a paper, it's Wong and Burrows this year, I think, in fact, people can look at. And there's a lot more stuff. I'm not going to show that. But I will oh, and this is where the fast flavor instabilities are happening. There's a lot of detail here, but we're starting to capture something that looks almost real. And these are the differences in the hydro response. And that was my focus. The neutrino signal is great, but I'm interested in whether it has an effect on the explosion. And these are the shock radii versus time. Dashed versus solid, not much difference here. Dashed versus solid, not much difference here. This is 1D models, but if you look in 2D, there are some little differences in when the thing explodes, and it can have an effect. And we're seeing whether what the systematic effects are. And then these are differences in the spectra. There's some interesting differences here. And this is the hydrodynamics. This is the entropy profile versus time versus radius. So the solid was with the oscillations, and the dashed the dashed is without the oscillations. And you see in the 1D cases, the differences are really minimal. This is a different model, but you can see that the position of the shock is a function of time, and all these sorts of things is about the same. Okay. And we have lots of these sorts of plots for different models, but for the models in 1D, no, there's no difference. In 2D, when things can explode and the shock radius is further out and there's some sort of turbulence, all of which is included in these considerations, there can be some differences. Here's the electron fraction versus time versus radius. And not much different. Now, electron fraction is relevant, particularly for nucleosynthesis when they explode, but this is a 1D model that doesn't explode. And this is a 2D model. So there are a lot of caveats. What I haven't shown also in the neutrino signal, particularly for the black hole formers, is there's oscillations. The shock is oscillating, and that oscillates the accretion. And you can see a modulation in the neutrino signal with a 70 hertz oscillation and a 15 hertz oscillation. So there are two different oscillations. One is a pulsating mode, and one is a standing accretion shock instability mode. It's a spiral mode that modulates the neutrinos when they form black holes. You don't get that sort of thing for most of the models because that effect is minimal and is overwhelmed by the neutrino heating. And after the explosion, there is no standing accretion shock instability at all, but there are a lot of neutrinos coming out. But there are some cases where that's an interesting adjunct to this. There's a lot of literature on this, and some of it is overemphasizes the so-called SASE, which isn't important in the early stages in any model, really. But at later stages, it can start to be important, and it's definitely visible in the neutrinos and the gravitational waves for the black hole formers that don't explode. Anyway, there are lots of caveats, and I appreciate your interest in this, and I'm here for questions. Thank you very much.
Thank you, Adams. That was very complete and nice summary. Any comments or questions?
Particularly on the neutrino stuff, because that's, I think, what the audience is assembled for. But anything is certainly game. Shlok.
Yeah, yes, Shlok.
Hi. Actually, I had two questions. The first one is, you said that one of the features of 3D simulations is that you can do a simultaneous analysis of both accretion and explosion. I'm
I
not able
didn't say
to.
analysis. I'm saying that both things happen simultaneously, and the net effect is due to the summed effects of those things, those phenomena.
Okay. So can you do this in 2D simulations as well? I cannot understand like why we cannot use 2D simulations for the same thing.
Well, 2D and 3D generally, if it explodes, they generally explode. The explodability is similar, but there's a symmetry in 2D that compromises the accretion. It can, and you can, and it also, you can't break it up in 3D. There are rings that won't break up in 2D, but the need to break up, they do break up in 3D, and it affects the accretion, it affects the explosions, affects the morphology, it affects a lot of things. The neutrino's signal is not much affected because it
Okay.
depends on the integrated neutrino signal. The nucleosynthesis, the explosion energies, the kick velocities are all different, and that's important to supernova people. Less important to people interested in neutrino emissions from core collapse. So
I see.
yeah, the 2D, now that we can do 3D, you shouldn't really look at 2Ds except for the integrated neutrino emissions, which we put online, those 100 models.
I see.
Danny,
Thank you.
yeah.
Yeah, I'm sorry, you were saying something.
No. Danny Milosavljevic has his hand up.
Oh, okay.
Hi, Adam. Obviously, I got a million things I could ask you. Maybe I'll pick your brain in Germany. More specific for this, you paint a wonderful image of just how complex everything is. One of the takeaways I have more recently is, those last neutrinos detected in 87.8 around 10 seconds. So
Yeah.
it just shows how long this inflow-outflow process, accretion, the energies continue on. If you want to comment on that, and then a follow-up, more SNEWS-related question is I'm in charge of the multi-messenger follow-up, which includes trying to get on Sky as quickly as possible with amateur observers around the world to try and observe shock breakout. So that timing from when the neutrino burst happens to when the shock emerges from the star has actually never been measured. We've seen the shock breakout signature. In 87.8, we measured the neutrino burst, but never had both measures. So I just wonder if you can comment on that time frame.
Yeah, that's directly connected to whether it's a stripped envelope supernova, a red supergiant, a yellow supergiant, etc. The times vary quite significantly, as you well know. I mean, from a day to less than an hour for the strip case. That strip case is going to be fast. So the blast wave, you have something that's the size of maybe 700,000 kilometers, but the blast wave is moving at a speed of 10,000 kilometers a second. And so you can see that you don't have much time in that case. So the time between the neutrinos and the breakout and the first light is a very stiff function of that progenitor. And so unfortunately, it varies quite a bit if you have just the neutrinos to make the prediction. And so there's a minimum time that could be fairly short, but you can estimate that pretty straightforwardly. Does that make sense?
How about the longest time? Some people have quoted, so
the
Dan
longest
Kaysen
time
said
is
days.
Yeah, it could. I mean, a really large supergiant, with a modest explosion will be more than a day to get to the surface. Even though it's asymmetrical, it's still going to take some time. And we have models that have shock velocities of 5,000 kilometers a second, not 10,000. And a lot of material is going even slower that's coming out. We have in David Vartanian's recent paper that was online last week or so. We have velocity distributions in X, Y, and Z projection of the ejecta, and the blast wave is just a little bit ahead of that for those models. The velocities are going to be different for the stripped envelope and the type 1b and C supernovae than for the red supergiant, even if the explosion energies are the same. But this is all sort of obvious, but this is what we're seeing too, particularly in David's calculations, where we've done 7 blasts to the surface and gone into the beginning of the supernova remnant phase.
Thank you, Adam.
All right. Yeah, getting back to the neutrino luminosity curves that you showed. I guess I mean, yeah, yeah, especially the one with the big electron neutrino luminosity in the very initial burst.
Yeah,
like, quite a bit later, actually.
Yeah.
Yeah, could be here. There was another one, but in any case, I mean, well, yeah, sorry. When you started talking about neutrino oscillations,
yeah,
because I guess once you start throwing in neutrino oscillations, and in a system like a supernova with all this stuff going on, I guess intuitively I would have thought that a fair amount of those electron neutrinos would have actually gotten oscillated away. So I'm a little bit surprised that
in the models, even with fast flavor instability, what emerges is still similar to what's there without oscillations as part of the mechanism. But as the neutrinos propagate down the density gradient, you get to a point where you can be MSW unstable.
Mm-hmm.
And so personally, I think that at the very least the envelopes make a difference. But by and large, these envelopes get to low enough densities in this neutrino oscillation context that you should have, at the very least, adiabatic MSW transformation. And so
so by the time the neutrinos get to the Earth, or just away from the supernova,
that's right.
How much of that initial
it could be quite significant, and we've published some papers on that. Other people have looked at this as well, and so that's why. I mean, that's a whole other subject, but that's an important subject because I think that what you're seeing here is what's emerging from the inner mechanism, but there's going to be a significant neutrino oscillation modification.
Okay. So that peak is there because you're still looking kind of inside of something.
For the normal hierarchy, the peak is down by a fair factor.
Yeah.
For the inverted hierarchy, the peak is still there. Right. But it's diminished a bit.
Yeah.
And that's if you assume adiabatic MSW transformation in the envelope of the star. You can have oscillations in the Earth as well. I mean, there's a lot of these little corrections, but the starting point is, I think, something like the models we're showing. And then through the star, you're going to get these MSW transformations. And the important thing is to have the multi-detector measurements so that you can actually, in the detectors, get what the species mix is from a simultaneous, compendious fit to all the data. The individual groups are going to want to show their results, et cetera, and they're going to be separate. But the real information is going to come from bringing together Juno and Dune and Hyper-K and the Gran Sasso results and IceCube and putting together a comprehensive model that has the neutrino emissions underlying it modified by the oscillations in a way that, because it's multi-parameter, but you have multiple detections, you'll be able to break the degeneracies. And so the international community, if he really wants to take full advantage of the neutrino data, has to really join forces. First of all, they have to be online. Then with all these data, they have to join forces eventually. They're not going to join forces in the beginning. Join forces eventually, so that because the different detectors are differentially sensitive to the different neutrino species, you'd be able to back out the original neutrino emissions and these sorts of things. It can connect directly with the mechanism models. So that modification of the neutrino signal, due to those things I've mentioned at the very least, is real. But the fact that we have multiple detectors, the Juno detector is sensitive to anti-electron neutrinos, the Dune detector is sensitive to electron neutrinos. There are subdominant channels that in some of these detectors you can actually measure. Some of these detectors can give you spectra. IceCube can give you a very nice light curve. That's the most sensitive light curves for the totals. And Super K, of course, and Hyper K have their own channel sensitivities. It's just going to take a lot of work to back that all out, but I think it's going to be worth it, and you're not going to have too many chances to do it.
Yeah, I agree on the necessity for the collaboration between all the experiments, obviously. But yeah, just to note, I mean, yeah, those subdominant channels can actually be decently significant too. I mean, Juno is going to have a pretty significant proton elastic scattering channel.
Yeah,
it's not quite as nice
also
as a flavor specific one, but it's pretty important.
Yeah, but there are many channels having in many of these species having to do with interaction with carbon, interaction with oxygen, neutrino electron scattering. You start to get in the weeds with the signals, but people aren't used to having thousands of events, which they're going to have.
Yeah. Yep.
And IceCube is going to have many more, but it's not going to know. It's just going to see a background variation.
Yeah.
As
okay,
people
thanks.
know. So there's a lot to unpack here. Andre.
Yes, thanks a lot for your presentation. I wonder if it's possible to estimate the effect of core collapse inside a binary star system. So if it affects the explodability and neutrino emission and all these parameters.
No. The thing that happens is that massive stars are predominantly in binaries. The number of people quoted is on the order of 70%. Some are close. We know that there have to be mergers. The binary interaction, even if there's not a merger, can affect things in a number of ways. One is that the orbital spin can be transferred to the star, and that might spin up the star and might spin up the core, and hence affect the rotation of the core, which we don't know have many constraints on, or any constraints on, effectively, right now. So that binary interaction affecting the spin is one thing. The other, and probably more important, is mass transfer. And so you transfer mass from the massive star to the companion, the primary to the secondary. If you do it early on, it'll change the evolution. If you do it later on, it matters when you do it. But transferring the matter will also change the radius of the object and how much mass you have to explode. And that'll change the timing between the neutrinos and the light. So there's a lot of things having to do with binary interaction that are important. The most dramatic is the merger. And it's possible that depending on when it happens, you will get the massive star cores to merge. We think that that's what happened in 87A. There's no, the evidence is from the rings and the nice work that's been done by Phil Podsiadlowski and collaborators over the years, sort of demonstrating that is a compelling story. But exactly what the core does when these two cores merge after only 20,000 or 10,000 years is not so clear. But I suspect it would have a radical effect on the inner core. And that's work in progress. 87A doesn't show obvious indications of being really exotic. It does look like it has an axis, but you get axis with standard neutrino explosions. So finding out what's left in this thing, I think, is rather key. And even then, we may not know. Any other questions?
Thanks a lot. So there are no detailed simulation for these effects at the moment.
Well, there are, but these effects are the effect on the compactness structure due to the binary evolution, due to some algorithm for mass transfer. David Vartanian led a paper in 2021 that used MESA and its capability to do mass transfer between stars and do two-star evolutions to see what the difference was in that particular scenario of mass transfer between the structure in the interior without and the structure interior with. And then we did 2D core collapse simulations to see what the differences were. But that was only very preliminary. You're right to highlight, though, the importance of importance of binary evolution effects, some of which I've articulated here, but it's an important thing going forward and very important for light curves and very important for the supernova population, how you get to type 1Bs and Cs and stripped envelope supernovae, how you get to 1B, 2Bs like Cas-A, etc. Because instead of having an 8 solar mass hydrogen envelope, you may have a 0.1 solar mass or a 1 solar mass hydrogen envelope. And that has a difference, that makes a difference in the supernova per se. Anyway, this is a large subject, which I can't summarize at this stage, but your question is very important.
Yeah, thank you. And one very short question. So in your models, when you have the black hole formation, so sometimes you have this formation during the simulation, and sometimes you have just a failed explosion,
That's right,
which will eventually lead to black hole formation. What would be the time scale of such formation, the maximum time scale? So what would be the duration of neutrino signal we would have from a failed supernova?
That would be for a very long time. We had a 12.25 and a 14 solar mass model not explode. And the accretion rates were such that it would take one of those models hours. And so certainly over a period of a number of minutes, you would have the neutrinos, I think, in both those cases. So the neutrino signal would continue. And then if the signal rate is large enough, and that depends on the distance and exactly what the accretion rate was, when the black hole formed, it's going to turn off abruptly. And we've had that prediction. I predicted that in the 1980s, that the neutrinos would just turn off. And that's not going to happen otherwise. And so if you see an abrupt turn off, then that's a signature of a black hole.
So it can last for several hours with
no, hours is hard because you have it's still diffusing energy out. It's not accreting much. It will accrete, but it's going to start getting accrete at lower and lower rate. It's just not going to explode. So that stuff is still falling in, and eventually it's going to form a black hole. The accretion rate is low enough that the accretion luminosity isn't very high at those later times. And it's basically just diffusion out of the core. And that diffusion is going to take tens of seconds. So that sort of thing, I would say tens of seconds, definitely. Maybe a minute. But the accretion gets so thin at later times that the m dot, GM over R m dot, is pretty small at later times and doesn't really distinguish this particular model so well. I mean, there's going to be some, but I think it's going to be pretty small.
I see. Thank you.
Yeah. And I'll also emphasize that if we see gravitational waves from these, and that's a completely different subject, there's a correlation in the emissions of between the gravitational wave emission and the neutrino emission. And for black holes, black hole formation, before the black hole forms, there's a characteristic neutrino signal. The average energies for one channel will be much higher than for others. You'll get gravitational waves that will also be modulated by these pulsations. This is all published, but we haven't emphasized it too much, but it's in the recent literature from our group. Okay, anything else? Marta?
I think the questions I had already been covered from my side. Yeah. Any other comments or questions?
There are a couple of questions in the chat.
No, I haven't been looking at the chat.
I see Slok with the hand.
Okay.
Can I go on? Or
Well, there's a radio pulse. There's a question that says expected a radio pulsar, or is the remnant a black hole? We don't know. There is some indication, and there's some work by Franson and collaborators very recently that they think they've identified a point source. They have some ideas about what is heating it. There's ALMA data that seems to have a point source. So there's starting to be indications that they're narrowing in on what's left. I don't want to pretend to know, but I think the easiest explanation is a neutron star. How fast it's rotating is not so clear, but it's not rotating very fast. It's not rotating fast with a high B field, because then you get the Crab pulsar energy deposition at 10 to the 38 ergs a second, and there's a limit of about 10 to the 34 ergs a second. So it's consistent with a cooling neutron star that is depositing its X-rays in the inner debris and heating up the material. But I'll refer to a very nice paper by Franson and collaborators, who's been following this very closely for decades.
okay, thank you.
Yeah.
Actually, I have an off-topic question. Can Phonex incorporate some the effect of some exotic particles as well, which might lead to some extra heating of the soul shock?
Yeah, no. I mean, years ago, I had a protoneutron star code that looked at the cooling of the thing, and I put in axions and Dirac neutrinos and right-handed neutrinos and things like this, and looked at the consequences to the signal in 87A. And yes, we can do that in this. It hasn't been a priority, but yeah. The axion stuff, if it's a DFS axion with a mass of 10 to the minus 6 to 1 eV, and the couplings are such that the mass and the coupling are correlated, we can put that in pretty quickly. We need the microphysics, and we need the inverse reaction of absorption of those particles if that happens. But yeah, it's really simple to do.
Okay, thank you. That's all.
Yeah. Yeah, and Kamal Raj, yeah, there's a lot more work that needs to be done, and yes, anybody who does so gets their hands dirty. The starting point is learning a lot of physics, being interested in the astrophysics, and yeah, the best people to do these sorts of things are not numerical people. It's physicists who like numerics. You can't do it as an applied mathematician. You can listen to them, but then you have to, as a physicist, you take it over, and then because if you don't understand what's going on and all those details and the physics, you will not make any real contributions of note. Marta, anything else? I feel a little guilty that we've gone over so much, but I felt I had to communicate some of the basics of the core collapse theory, because most people in the world that are following this aren't following this. And I find that when I give these talks, people are blown over by the difference between what they thought was the case and what they thought was the current status of theory, and what I communicate is what I think is the current status of theory. It's very different. And
yeah, it was great to hear all these updates and know what's going on this direction.